The sun you know isn't the sun you think. On a clear night, if you lie back and stare long enough at the sky, you can start to feel it. The weight of the distance, the sheer incomprehensibility of what's out there. Every single point of light is an entire sun. A raging nuclear furnace burning at millions of degrees, blasting radiation in every direction for millions or billions of years. Most of those stars are so far away that even if one of them exploded right now, the light from that explosion wouldn't reach us for tens of thousands of years. The night sky is not a view of the universe as it is. It's a layered composite of how different parts of it used to be, across thousands of different past moments, all arriving at your eyes simultaneously. It is a genuinely strange thing to sit with once you let it settle. The star you're looking at in one part of the sky might be showing you its light from 400 years ago, while the star next to it in the sky, appearing equally close, is showing you light from 40,000 years ago. They appear side by side. They are separated in time by the entire span of recorded human history, multiplied many times over. Astronomy is the only science where simply looking at your subject is an act of time travel, and the further you look, the further back in time you go. The closest star to us, our own sun, feels impossibly big from where we stand. Its diameter is about 1.4 million kilometers. More than 1 million Earths could fit inside it. It holds 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid and comet put together barely registers as a rounding error. The gravity it generates reaches past Pluto, past the scattered disk, past the outermost fringes of the Oort cloud, tethering comets that won't return for tens of thousands of years. And yet, against the backdrop of what the universe has actually produced, our sun is unremarkable. It is a thoroughly average star, medium mass, medium temperature, medium brightness. Astronomers classify it as a G-type main sequence star, sometimes informally called a yellow dwarf, and in the galactic neighborhood, it sits comfortably in the middle of every important distribution. There are stars much smaller and dimmer. There are stars much larger and brighter. And then there are the giants, scattered across the Milky Way and in the galaxies beyond it. There are stars so enormous that comparing them to the sun is almost meaningless. Stars where the numbers become too large to grasp without something to anchor them to. Stars where the word big stops applying and something more extreme is needed. These are the red supergiants, the hypergiants, the monstrous endpoints of stellar evolution where gravity and nuclear physics have pushed matter into configurations that, for most of human history, we didn't even know were possible. To give you a concrete sense of where this is going, the largest known star is estimated to be roughly 2,150 times wider than our sun. If the sun were the size of a golf ball, this star would be roughly 60 meters across, taller than a 20-story building, wide enough that you couldn't throw something from one side to the other. A golf ball sitting at the foot of a skyscraper. That's the scale of what we're dealing with. Some of these stars are dying in slow motion. Some have already become almost unrecognizable compared to what they were millions of years ago. All of them will end in the most violent ways the universe provides. How stars grow, the mechanics of expansion. Before we meet the monsters, it helps to understand why some stars grow so enormous in the first place, because the mechanism is stranger and more counterintuitive than most people expect. Stars are born in vast clouds of gas and dust called nebulae. Gravity begins pulling pockets of this material together, and as the density increases, the pressure at the center climbs. Temperature climbs with it. After millions of years of gradual inward collapse, the core reaches the threshold where hydrogen nuclei can begin fusing into helium, At that point, a star ignites. The energy released by nuclear fusion pushes outward, creating a pressure that counteracts the inward pull of gravity. This balance, the crushing weight of the star's own mass pressing down against the outward pressure of nuclear fire, is what holds a star together and defines its basic character for most of its working life. More mass means more gravity pressing inward. To counterbalance that, the core has to burn hotter and faster, which means it consumes its hydrogen fuel more rapidly. This creates one of the most counterintuitive rules in astronomy. The more massive a star is, the shorter its life. Our Sun will burn for about 10 billion years in total, and it's currently about halfway through that span. A star with 10 times the Sun's mass will exhaust its core hydrogen in around 20 million years, 500 times faster. A star with 50 times the Sun's mass might survive only a few million years before its internal structure starts failing. For decades, astronomers catalogued these facts on a diagram called the Hertzsprung-Russell diagram, named after the Danish astronomer Einar Hertzsprung and the American Henry Norris Russell, who independently developed it in the early 20th century. It plots stars by their temperature against their luminosity, and what emerges is a pattern. The vast majority of stars fall along a diagonal band called the main sequence, running from cool, dim, red stars in the bottom right to hot, bright blue stars in the upper left. Our Sun sits near the middle of that band. The stars we'll be visiting today, the red supergiants and hypergiants, appear in the upper right corner, and the most massive stars we'll discuss sit at the extreme upper left. These two corners represent opposite ends of stellar extremity. One, the product of enormous age and expansion, the other the product of almost unimaginable mass and temperature. When a massive star runs low on hydrogen in its core, something dramatic happens. The core contracts and heats up further, triggering new fusion processes that generate even more energy. All of that additional energy has to go somewhere. It goes outward. The star's outer envelope begins to expand, not by a factor of 2 or 3, but often by factors of hundreds or even thousands. As those outer layers expand, they cool. Cooling shifts the star's color from the white-blue of a hot young object toward orange, and then deep red. The star has become what astronomers call a red supergiant. At the most extreme end, it becomes a red hypergiant. Here is the key insight that reverses most people's assumptions. The largest stars are red because they are old and dying. They are not young and energetic. They are bloated and exhausted, in the process of consuming their last fuel reserves, puffed up to extraordinary sizes as their cores perform increasingly desperate nuclear alchemy. A red hypergiant is not a star at its peak. It is a star near its end. This is also why red supergiants are relatively rare. They represent only a brief phase in a massive star's total lifespan, perhaps a few 100,000 years out of a total of several million. The universe is full of long-lived, modest main sequence stars that will burn steadily for billions of years. The giant, bloated, dying stars are passing through a narrow window of time, and catching one in that state requires a universe large enough and active enough that somewhere, at any given moment, one of them is in that phase. Ours is, and so they exist, and we can observe them. One problem is that the numbers involved in describing these stars are genuinely difficult to hold in mind, and there's a real risk of everything blurring together. To keep comparisons grounded, it helps to return to a single reference point: the distance from Earth to the Sun, about 150 million kilometers, which astronomers call one astronomical unit. The Sun's radius is about 0.005 astronomical units. The red hypergiants have radii of around 6 to 11 astronomical units. R13601, the most massive star known, has a radius of only about 0.2 astronomical units, but contains nearly 300 times the Sun's mass. Size and mass tell very different stories, and both are worth following. The Garnet Star, a giant in our own backyard. At about 2,400 light-years away, in the northern constellation of Cepheus, there's a star visible to the naked eye under good conditions. Not bright enough to be prominent, it sits at around 4th magnitude, easy to miss unless you know what you're looking for, but unmistakable once you've found it. The English astronomer William Herschel noticed it in 1781 and wrote about it with unusual enthusiasm. He described it as having a deep, rich, distinctly red color, unlike almost anything else in the sky. He called it a very fine deep garnet color, and the name stuck through the centuries. Today, it's officially known as Mu Cephei, but almost everyone who studies it calls it the Garnet Star. Mu Cephei is a red supergiant, and its size is difficult to render in ordinary language. Its radius is estimated at somewhere between 1,000 and 1,650 times that of the Sun, depending on which measurement technique is being used and which distance estimate you trust. The range in those numbers doesn't mean the measurements are unreliable. It reflects the genuine challenge of measuring a star that is 2,400 light-years away, has no hard surface, pulsates in size over months to years, and is partially surrounded by its own ejected material. If placed where our Sun is, Mu Cephei's surface would extend well past the orbit of Mars and approach the orbit of Jupiter. Every planet in the inner solar system, Mercury, Venus, Earth, and Mars, would be completely submerged. You could fit around 250 million suns inside the volume it currently occupies. Its luminosity exceeds 100,000 times that of the Sun in visible light, and because so much of its radiation emerges as infrared heat rather than visible light, the total energy it emits is considerably higher. Its surface temperature is around 3,500 Kelvin, compared to the Sun's 5,778 Kelvin. That relative coolness is precisely what gives it the deep red-orange color Herschel admired. The physics is direct. The cooler the surface temperature of a giant star, the further its outer layers have expanded from the nuclear burning interior, and the redder and cooler those outer layers appear. Temperature and color in stars are not independent aesthetics. They are the same physical fact expressed in different ways. The Garnet Star is also a variable star, meaning its brightness changes over time. It wobbles between roughly magnitude 3.4 and 5.1 over irregular periods of several hundred days, pulsating slowly as its outer envelope expands and contracts. These pulsations are not orderly or predictable. They are the signature of a star in a turbulent late phase of its existence. Mu Cephei is no longer the stable hydrogen-burning machine it once was. Its core is now fusing heavier elements, working through an increasingly rapid succession of nuclear processes as it approaches the end of what it can sustain. What surrounds the Garnet Star adds another layer. A shell of dust and gas extends out to around 15,000 astronomical units from the star's center, more than 200 times the distance from the Sun to Pluto. That shell has been building for 2,000 or 3,000 years, formed from material the star shed through its stellar wind, and it carries the molecular signatures of the star's interior chemistry out into the surrounding interstellar medium. This is what old massive stars do as they age. They blow themselves apart slowly, dispersing enormous quantities of processed material long before any final catastrophic event. Mu Cephei is also a runaway star. It's moving through space at an unusually high velocity relative to the stars around it, most likely because it was gravitationally ejected from its birth cluster by an earlier interaction with another massive object. It carries that history with it through the galaxy, trailing dust and enriched gas behind it. In the broader context of stellar extremes, Mu Cephei is a substantial giant, but not the very largest. It's an effective starting point because it's close enough and bright enough to have been known for centuries, sits in the northern sky where a large fraction of the world's population can observe it, and illustrates clearly what the red supergiant category looks like: enormous, variable, dying, and already enriching its surroundings. Betelgeuse, the star that made headlines. Some stars have achieved a degree of cultural recognition that goes far beyond their astrophysical significance. Betelgeuse is one of them. It marks the left shoulder of the constellation Orion, or the right shoulder, depending on which way you imagine the hunter to be facing. And it burns with a distinctive orange-red glow that stands out even in moderately light-polluted skies. It's the 10th brightest star in the entire night sky. It has been named, observed, and written about by civilizations going back to ancient Egypt, Mesopotamia, and classical China. The name most people use for it today is a corruption of an Arabic phrase referring to the hand or armpit of the giant, filtered through several centuries of medieval translation, in which Arabic letters were misread and the meaning drifted considerably from the original. Betelgeuse sits about 650 light-years from Earth, making it the closest red supergiant to our solar system. That proximity has made it one of the most intensively studied stars in the sky. It's one of only a handful of stars beyond the Sun for which the physical disk has been directly resolved, photographed as a disk rather than a point, using high-resolution interferometry. Its radius is approximately 700 to 1,000 solar radii, depending on the epoch and technique. At its largest, its surface would extend past the orbit of Jupiter. It contains somewhere between 16 and 19 solar masses and shines with roughly 100,000 times the Sun's luminosity. The surface of Betelgeuse, as seen in the best interferometric images, is not uniform. It shows large, bright patches, the signatures of enormous convective cells, each one comparable in size to the entire inner solar system, rising from the interior, carrying hot plasma toward the surface, then cooling and sinking back down. These cells drive the variability that makes Betelgeuse appear slightly different every time you observe it with sufficient resolution. In late 2019, Betelgeuse did something that sent a wave of excitement through the astronomical community and simultaneously captured the attention of hundreds of millions of people who had never previously given a moment's thought to stellar physics. It dimmed dramatically. Its brightness fell by roughly 60% between November 2019 and February 2020, dropping from its usual position among the 10 brightest stars in the sky to outside the top 20. Speculation exploded. Was Betelgeuse about to go supernova? Was the most famous variable star in the sky about to put on the most spectacular show since the supernova of 1604, which Kepler observed and which was visible in daylight for weeks? The answer turned out to be no, though the real explanation was compelling in its own right. Convective shocks deep inside the star generated an enormous outflow of plasma, bringing superheated material to the surface and ejecting it outward. As that material traveled away from the star and cooled, it condensed into a vast cloud of dust particles, each one smaller than a grain of beach sand. That cloud drifted across the line of sight between Betelgeuse and Earth, blocking roughly a quarter of the star's visible surface from our perspective. By April 2020, Betelgeuse had returned to normal brightness as the dust dispersed. Not a supernova, a massive stellar belch that happened to blow debris across our view. The Great Dimming Event taught astronomers something valuable. It showed, in real time, the kind of violent ejection process that gradually strips the outer layers from aging massive stars over their final 100,000 years of life. The event was not the beginning of the end. Betelgeuse is expected to persist for tens of thousands to perhaps 100,000 more years before its core finally collapses. But it demonstrated that these stars are not quietly fading. They are actively, dynamically shedding themselves into surrounding space. When Betelgeuse does finally go, the visual consequences for Earth will be extraordinary. At peak brightness, the supernova will shine somewhere between the brightness of the half moon and the full moon. A single point of orange-red light in Orion, visible in broad daylight, remaining bright enough to see with the naked eye for weeks before slowly fading over following months. The familiar shape of the Orion constellation will be permanently altered. Eventually, all that will remain at that location is an expanding cloud of glowing gas, a supernova remnant, growing and thinning for tens of thousands of years. In July 2025, astronomers confirmed something that had been suspected for years. Betelgeuse is not alone. A small companion star, nicknamed Betelbuddy, was detected using the Gemini North Telescope. The companion appears to be a young, roughly sun-sized star, completing one orbit in about 6 years. Its presence explains some of Betelgeuse's longer period brightness variations that had previously resisted explanation, and raises new questions about how the eventual supernova might unfold. Betelgeuse has been studied intensively for decades, and it is still revealing new layers. VY Canis Majoris, the Great Dogs Monster. South of Orion, in the constellation of Canis Major, also referred to as the Great Dog, there is a star first noted by the French astronomer Jérôme Lalande in 1801. He recorded it as a 7th magnitude object and moved on. Through the 19th century, observers described it as a deep crimson, and several reported what appeared to be multiple stellar components surrounding it. Those components turned out to be something far stranger: bright, dense patches in an enormous cloud of gas and dust surrounding the star, glowing with the star's own reflected light. VY Canis Majoris, or VYCMA, is one of the most extreme stars ever catalogued. With a radius of approximately 1,420 times that of the Sun, its diameter stretches across roughly 13 astronomical units. That's the distance between the Sun and Saturn measured from one side to the other. If placed at the center of our solar system, its outer atmosphere would engulf every planet out through Jupiter. Light, traveling at 300,000 kilometers per second, would take around 16 hours to travel from one side of this star to the other. But raw size barely captures what makes VYCMA remarkable. It's a profoundly turbulent object. It is losing mass at an average rate of about 6/10,000ths of a solar mass per year, compared to the Sun's rate of mass loss. That's roughly 1 billion times higher. During peak ejection events, the rate climbs even further. Over its roughly 8 million year lifetime, VYCMA has probably shed close to half of its original mass, dispersing it into surrounding space in a series of violent outbursts that have left traces readable like a geological record. The Hubble Space Telescope has captured extraordinary images of VYCMA's surrounding material. Rather than a smooth, symmetric shell of ejected gas, the images show an intricate tangle of filaments, arcs, dense clumps, and loops, each structure corresponding to a different ejection event from a different era. One large arc to the northwest was blown out roughly 400 years ago, moving at around 50 kilometers per second. Other structures trace back 800 to 1,000 years. Several dense knots near the star were ejected only 100 to 200 years ago. This star has been erupting throughout the history of the Ottoman Empire, the Renaissance, the Scientific Revolution, and the Industrial Revolution. And none of the humans alive during those eras had any idea they were living in the light of one of the most active stellar objects in the galaxy. Each of those knots and arcs carries a record. The chemical composition of the ejected material, the velocities at which it's moving, and the geometry of its distribution all encode information about what was happening inside VYCMA at the moment of each ejection. It's a kind of stellar archaeology, reconstructing the star's inner history from the material it has scattered into the space around it. The surrounding nebula is so bright that it was first detected in 1917 using only a modest 18-centimeter telescope, despite being nearly 4,000 light-years away. For decades afterward, the bright patches within it were catalogued as companion stars, before later analysis revealed their true nature. The nebula stretches to about 12,000 astronomical units from the star. Despite VYCMA shining with roughly 270,000 times the sun's brightness, the obscuring cloud means it cannot be seen with the naked eye from Earth. All that light is absorbed and re-radiated by the surrounding dust, emerging mostly as infrared radiation. VYCMA is also a maser source, masers being the microwave equivalent of lasers, producing intense coherent beams at very specific frequencies. Inside the cloud surrounding VYCMA, molecules of silicon monoxide, water vapor, and hydroxyl are energized by the star's radiation and respond by emitting powerful microwave signals clear across nearly 4,000 light-years of space. Studying these maser emissions gives astronomers a kind of three-dimensional map of the ejection history, tracing the geometry and velocity of material at different distances from the star's center. Based on its mass and evolutionary state, VYCMA may produce not a conventional supernova, but a hypernova, an explosion releasing many times the energy of a typical stellar death, accompanied by intense long-duration gamma-ray bursts. At nearly 4,000 light-years, Earth is completely safe. But when it comes, VYCMA's death will produce a brilliant new point of light visible in daylight for days to weeks. Eta Carinae, the star that erupted in living memory. Not all extraordinary stars age quietly. Some give dramatic previews. In the southern constellation of Carina, roughly 7,500 light-years from Earth, there is a binary star system called Eta Carinae. The primary star is one of the most massive and luminous objects in the Milky Way, estimated at between 100 and 150 solar masses, blazing with approximately 5 million times the Sun's luminosity. Unlike the cool red supergiants, Eta Carinae's primary is extremely hot and compact. Its surface temperature is around 25,000 Kelvin, and its radius is only a few hundred times that of the Sun. What it lacks in physical volume, it more than compensates for in raw energy output. What makes Eta Carinae extraordinary in the context of stellar history is an event that astronomers actually witnessed in real time. Between 1837 and 1856, the system underwent a series of violent eruptions. In 1843, it briefly became the second brightest star in the entire night sky, surpassed only by Canopus, despite being 7,500 light-years away. People in the southern hemisphere could see it without any optical aid. Then it faded back over the following years. This event, now known as the Great Eruption, released energy comparable to a supernova, and yet the star survived. During the eruption, an estimated 10 to 20 solar masses of material was ejected in just a few decades. The material from that eruption is still expanding outward today and clearly visible in modern telescopic images. The Homunculus Nebula, a two-lobed structure of ejected gas and dust resembling a peanut or hourglass from the right angle, contains the debris of that 19th century explosion, expanding at around 650 kilometers per second. Each lobe spans several light months across. The entire structure has been extensively studied with Hubble and other instruments, and stands as the most directly documented violent non-supernova stellar outburst in historical astronomy. Why Eta Carinae erupted the way it did is still not fully understood. The most widely accepted model involves the binary companion, which orbits the primary in a highly elongated ellipse, approaching and retreating every 5.54 years. The gravitational and radiative interactions at closest approach are thought to drive the instabilities that cause these mass ejections. The primary is operating at or above the Eddington limit, the threshold at which radiation pressure exceeds gravity, and does so periodically in ways that resist simple modeling. Eta Carinae is considered one of the leading candidates in the galaxy for the next hypernova. When it does explode, the resulting gamma-ray burst, if oriented toward Earth, could cause meaningful damage to the ozone layer. Not an extinction event at this distance, but a genuine reason to keep close watch on it. It is the neighbor who has already shown a tendency for extreme behavior. VY Scuti and the measurement problem. For years, the title of the largest known star was confidently held by VY Scuti, a red hypergiant in the constellation Scutum, the Shield, lying about 5,900 light-years from Earth. First catalogued in 1860 at the Bonn Observatory, it attracted little attention for most of the following century. Then, better measurements of its angular size and estimated distance suggested a radius of around 1,700 times that of the Sun, and it achieved a level of public recognition that far exceeded most astrophysical objects. Videos and infographics spread widely. It became the go-to example for how small our Sun really is. The numbers made for compelling presentations if VY Scuti had a radius of 1,700 solar radii. It would extend past Jupiter's orbit. Around 5 billion suns could fit inside it. Light would take around 7 hours to travel around its equator once. The numbers were genuinely staggering, and they weren't fabricated. They were the best available at the time. Then, the Gaia Space Observatory entered service. Launched in 2013, Gaia spent years mapping the precise positions and motions of over 1 billion stars, producing the most accurate stellar distance catalogue ever compiled. Its measurement of VY Scuti's parallax, the tiny shift in apparent position caused by Earth's orbit around the Sun, placed the star closer than previously thought, at around 5,100 light-years rather than 5,900. A closer distance meant a smaller derived radius. Different analyses converged on values between about 755 and 909 solar radii, still enormous, but substantially smaller than the record-breaking figure that had defined the star's reputation. This is not a story about astronomers making mistakes. It is a story about the genuine difficulty of the problem. The angular diameter of VY Scuti, as seen from Earth, corresponds to trying to measure the apparent size of a marble placed 250 kilometers away. The measurements are necessarily indirect, combining distance estimates with angular diameter observations and spectral temperature analysis, each carrying its own uncertainty. For a pulsating variable star at the extreme end of what instruments can resolve, the margin of error around any central estimate is substantial. The original 1,700 solar radii figure was reasonable given the technology of the time. Gaia gave a better answer. What this illustrates at a deeper level is that the rankings at the very top of the stellar size scale are genuinely contested and will remain so until instruments improve further. Several of the stars in contention for the top spots have size estimates that overlap within their margins of error. The largest known star is a title that has passed between candidates more than once, depending on which measurements you trust and when you're asking. What we can say with confidence is that there is a category of objects, the red hypergiants, that occupies the extreme end of the size distribution, dramatically larger than everything else, existing at the physical boundary of what stellar evolution appears to allow. Stephenson, 2-18, the current record holder. In the constellation Scutum, roughly 19,000 light-years from Earth, sits the star that currently holds the largest known radius of any stellar object. Part of a cluster discovered by the American astronomer Charles Bruce Stephenson in 1990, it's designated Stephenson 2-18. Also catalogued as RSGC 2-18 in other surveys. The name has no poetry in it, but the object behind it is extraordinary. By the best current estimates, Stephenson 2-18 has a radius of approximately 2,150 times that of the Sun. If those numbers are correct, this is the physically largest star known to exist. To try to visualize it, if it occupied the position of our Sun, the surface of Stephenson 2-18 would extend more than halfway to Saturn. Jupiter's orbit would be buried inside it. The Earth would be so deep within the star that Saturn's orbital distance would not yet have reached the surface. The Sun itself, sitting next to this object, would look like a marble placed at the base of a 20-story building. Its luminosity is estimated at around 440,000 times that of the Sun, though this number depends heavily on the assumed distance and the correction applied for interstellar dust, which absorbs a significant fraction of the star's light before it reaches us. Because most of its radiation is emitted in the infrared rather than visible light, it is invisible to the kinds of observations that catalogued the familiar naked-eye stars of the night sky. It only appears in infrared surveys capable of penetrating the dust that lies between us and the galactic center. The cluster in which Stephenson 2-18 sits has its own claim to being remarkable. The Stephenson 2 cluster contains at least 26 confirmed red supergiants in close proximity, the largest known concentration of such stars anywhere in the Milky Way. These objects formed together from the same vast molecular cloud, evolved in parallel, and their collective aging has produced a unique laboratory for studying the end stages of massive star evolution. Nowhere else in the observable galaxy are so many of these enormous, dying stars crowded together in one place. The 2,150 solar radii estimate sits uncomfortably close to or beyond the theoretical upper limit for red supergiant sizes. Current stellar evolution models suggest that a red supergiant's outer envelope becomes too loosely bound to remain coherent above about 1,500 to 2,000 solar radii. Beyond that, the outer layers should disperse rather than continue expanding. If the current estimate is right, Stephenson 2-18 either slightly exceeds that theoretical ceiling, the models need adjustment, or both. This productive tension drives ongoing research, and the star is a key target for the next generation of infrared-capable large telescopes. UU OHG 64, a giant in another galaxy. Most of the stars we have discussed today live in the Milky Way, but our galaxy is not alone. Orbiting it as a satellite is the Large Magellanic Cloud, a smaller companion galaxy about 163,000 light-years away, visible from the southern hemisphere as a faint smudge near the southern celestial pole. It contains hundreds of millions of stars, and among them is a red hypergiant that holds a significant place in the history of stellar observation. WOHG 64 is located in the constellation Dorado, deep within the Large Magellanic Cloud. Its estimated radius is approximately 1,540 solar radii, placing it comfortably among the very largest stars known, though uncertainty in this number is substantial. Different analyses span a wide range. It is surrounded by a torus of dense dust that absorbs most of its visible light, making it accessible mainly in infrared observations. In 2024, astronomers using the Very Large Telescope Interferometer in Chile produced the first direct interferometric image of a star outside the Milky Way. The subject of that historic observation was WOHG 64. The resulting image resolved the structure of the dust torus surrounding the star, confirming its elongated geometry and pole-on orientation. This was a genuine milestone, the first time any stellar object in another galaxy had been directly resolved, made possible by the extraordinary baseline of the interferometer and the relative proximity of the Large Magellanic Cloud compared to more distant galaxies. WOHG 64 also appears to be undergoing a dramatic transition. Observations spanning 3 decades showed a notable change in its variability around 2014. And some researchers interpret the spectroscopic evidence as a shift from a red supergiant to a yellow hypergiant phase. A hotter, more compact configuration in which the outer layers stop expanding and begin to contract. Other analyses contest this, and as of 2026, the debate remains active and unresolved. This makes WOHG 64 one of the most intensively observed individual stars in any external galaxy. One practical advantage of its extragalactic address is that all stars within the Large Magellanic Cloud are at essentially the same distance from Earth, eliminating the main source of distance uncertainty. The error bar on its luminosity and derived radius is therefore smaller than for many comparable stars in the Milky Way, where distances span a range of thousands of light-years and must be individually estimated. The difference between large and massive. A clear pattern has emerged through the stars we've visited. The physically largest are cool, red, and diffuse, their mass spread across enormous volumes. But there is a crucial distinction between a star that is large by volume and a star that is massive by total content. And these two qualities point in completely opposite directions when pushed to extremes. Red hypergiants like VY and Stephenson 2-18 contain roughly 15 to 30 solar masses spread across volumes billions of times larger than the Sun. The outer layers of these stars are so thinly populated with gas that the average density in those regions is lower than Earth's atmosphere at sea level. These stars are, paradoxically, less dense than the air you're breathing in their outermost regions, despite containing tens of times the Sun's mass. Their enormity is a consequence of expansion at the end of life, not accumulation. The most massive stars concentrate their mass in a tight, ferociously energetic package. Their radiation pressure prevents the outer envelope from expanding the way a cool star's does. They remain physically compact even as they pour out unimaginable quantities of energy. They appear blue-white, not red, because their surfaces are at tens of thousands of degrees rather than a few thousand. This distinction sits at the heart of a concept called the Eddington limit, named after the British astrophysicist Arthur Eddington, who worked out the relevant physics in the early 20th century. As a star grows more massive, it generates more luminosity. That luminosity carries radiation pressure, light physically pushing outward on the star's gas. Above a certain mass threshold, the radiation pressure overcomes the inward pull of gravity and begins blowing the outer layers away. The star can no longer accumulate more material. Traditional estimates placed this ceiling at around 150 solar masses. Then astronomers found a star that appears to weigh nearly 300 solar masses. R136A1, the star that shouldn't exist. Around 163,000 light-years from Earth, inside the Tarantula Nebula in the Large Magellanic Cloud, there is a dense cluster of young, hot blue stars called R136. When it was first catalogued, astronomers thought it might be a single star containing perhaps 1,000 solar masses. So extreme, it seemed to violate everything known about stellar physics. It was only in 1985 when speckle interferometry allowed the cluster to be resolved into individual components that the most extreme object within it, R136A1, turned out to be a single star remarkable enough on its own. R136A1 is currently the most massive and luminous star known to science. Its mass is estimated at around 291 solar masses. At birth, it may have weighed somewhere between 320 and 350 solar masses. It shines with a luminosity of approximately 7.2 million times that of the Sun. Its surface temperature exceeds 46,000 Kelvin, more than 8 times hotter than the Sun, which is why it blazes as a blue-white point rather than the typical deep red of the hypergiants. It takes no more than 4 seconds for R136A1 to release more energy into space than the Sun will produce in an entire year. Its physical radius is only about 43 times that of the Sun, large by ordinary standards, but a tiny fraction of the volume occupied by a red hypergiant. This is what extreme mass looks like when it hasn't been stretched out by expansion. Concentrated, hot, dense, and ferociously energetic. Every year, it sheds roughly 1/6000th of a solar mass through its stellar wind, about 1 billion times more mass loss than the Sun experiences annually. Since forming roughly 1 million years ago, R136A1 has already lost an estimated 55 solar masses. It is literally dissolving itself into space as it burns. The Tarantula Nebula, in which R136 sits, deserves its own moment. It is the most productive and extreme star-forming region in the local group, the collection of galaxies that includes the Milky Way and its neighbors. It spans roughly 600 light-years across and contains some of the most massive and luminous stars known, including not just R136A1, but dozens of other stellar objects that would hold records in quieter galactic neighborhoods. The nebula glows with an intensity that makes it visible to the naked eye from Earth as a faint haze at 163,000 light-years, an almost incomprehensible feat of sheer luminosity. If it occupied the same position in the sky as the Orion Nebula, about 1,300 light-years away, it would span 60 full moon diameters across the night sky and be bright enough to cast visible shadows. R136A1 alone accounts for roughly 7% of the entire Tarantula Nebula's ionizing radiation output. This single star, out of the thousands within the nebula, dominates the radiation environment of a structure spanning hundreds of light years. Its stellar wind has carved a visible cavity in the surrounding gas, sculpting the nebula's internal structure from its position near the center of the R136 cluster. For a star above the theoretical 150 solar mass Eddington ceiling to exist at all, some process must have allowed it to accumulate more mass than the radiation pressure threshold should permit. The most widely accepted explanation is a stellar merger, two or more massive stars in a dense young cluster colliding and combining early in their lives before they had time to move apart. At the extreme densities found near the core of young massive clusters, such mergers are now thought to be a regular rather than exceptional occurrence. The R136 cluster formed only about 1 to 1.5 million years ago, and it contains at least 72 extremely massive stars with luminosities ranging from 1.5 to 4.7 million times the Sun. The R136 cluster as a whole represents something astronomers call a superstar cluster, a concentration of stellar mass and luminosity that has no counterpart in quieter regions of the galaxy. In more typical spiral arms like the one our solar system occupies, massive stars form in smaller, more dispersed groups, separated by light years. In regions of intense star formation like the Tarantula Nebula, the density and intensity of the process produces objects that push the boundaries of what formation models predict. The R136 cluster packs more mass and more luminosity into a smaller volume than almost any comparable structure known in the local group. The Tarantula Nebula itself is worth pausing on, because the scale of it puts even R13601 in context. The nebula is an HII region, a vast cloud of hydrogen gas energized by the ultraviolet radiation of hot young stars within it, causing the hydrogen to glow with a characteristic pinkish-red emission. It spans roughly 600 light-years across, which means that light takes 600 years to cross from one side to the other. The entire distance from Earth to Betelgeuse, 650 light-years, is comparable to the width of this single nebula. Within that volume, star formation has been ongoing for millions of years, producing multiple generations of stars and star clusters, each one enriching the gas around it with the products of stellar evolution and triggering further rounds of compression and collapse. The nebula takes its name from its appearance in long-exposure photographs, where the tangled bright filaments and dark dust lanes form a pattern that 19th century astronomers thought resembled the legs of a spider. It was first noted as a nebulous object by Nicolas Louis de la Caille in 1751 during his survey of the southern sky from the Cape of Good Hope, and it has been studied continuously ever since, growing in significance with every generation of instruments that has turned its attention there. The Hubble Space Telescope alone has produced dozens of deep-field images of different regions within it, each revealing new levels of complexity, clusters within clusters, pillars of gas being eroded by nearby stars, shock fronts where supernova remnants are colliding with denser gas, and young stellar objects so recently formed that they haven't yet blown away the dust clouds in which they were born. R136 itself sits near the heart of the nebula, and its intense radiation is the main driver of the ionization that makes the tarantula glow. Observations with Hubble have resolved the cluster down to individual stars, revealing a population density near the center that is extraordinarily high. Thousands of stars packed into a volume only a few light-years across. This density creates the conditions for the interactions and mergers thought to have produced R136A1 and its most massive neighbors. It also means that the stars in the cluster are constantly influencing each other through tidal forces and radiation, producing a dynamical environment, nothing like the relatively isolated neighborhood our own Sun occupies. For Wolf-Rayet stars, the category R136A1 belongs to the mass loss rates are so extreme that the star is literally redefining its own properties on observable timescales. Wolf-Rayet stars were first identified in 1867 by the French astronomers Charles Wolf and Georges Rayet, who noticed that certain stars had unusually broad emission lines in their spectra, the signature of gas moving at extreme velocities. Those broad emission lines are produced by the stellar wind itself, moving outward at thousands of kilometers per second and colliding with slower material further out. The wind from R136A1 is so powerful that if you were in the surrounding Tarantula Nebula and somehow safe from the radiation, you'd feel a continuous gale of plasma, not the gentle pressure of our Sun's solar wind, but something orders of magnitude more intense. If R136A1 were placed where the Sun is, the consequences would be immediate and absolute. Its mass would compress Earth's orbital year from 365 days to approximately 3 weeks. Its radiation would flood every square meter of Earth's surface with a flux tens of thousands of times higher than what we receive from the Sun. No atmosphere, no ocean, no chemistry, no rock on the surface would remain recognizable. It is an object that defines an opposite pole of habitability from everything we take for granted about our own star, and a reminder that the universe produces environments covering a range so vast that the conditions we live in represent a narrow and fortunate sliver at one end. How these stars die. Both categories of extreme stellar objects, the physically largest and the most massive, are temporary. Their extremity is a phase in a story that ends in the most dramatic fashion the universe provides. For red hypergiants like VY and Stevenson 2-18, the final chapter has been underway for a long time. They are losing mass continuously, their outer layers dispersing into the surrounding interstellar medium through stellar winds and episodic eruptions. Over timescales of tens to hundreds of thousands of years, this mass loss will strip away much of what currently makes them so physically enormous. Stripped of their outermost layers, these stars will compact and heat up, evolving through categories like luminous blue variable and Wolf-Rayet star, before their cores exhaust their fuel reserves and collapse. Consider what that post-death landscape looks like. When a red supergiant of moderate mass, say around 10 to 20 solar masses, finally collapses, the core rebounds and sends a shockwave outward through the star's outer layers. That explosion disperses the outer shell of gas and dust that the star has been patiently building for hundreds of thousands of years, adding fresh energy to material that was already drifting slowly outward. The result is a supernova remnant, a rapidly expanding shell of glowing ionized gas that grows and fades over thousands of years. The Crab Nebula, visible in the constellation Taurus and one of the most extensively studied objects in the night sky, is the remnant of a supernova observed by Chinese and Arab astronomers in 1054 CE. At its center, a rapidly spinning neutron star, the collapsed core of the original massive star, compressed to a sphere roughly 20 kilometers across, still powers the nebula's glow nearly 1,000 years later, spinning 30 times per second and radiating energy across the electromagnetic spectrum. At higher progenitor masses, the remnant may be a black hole rather than a neutron star, an object where the collapse has proceeded past even the nuclear density floor, squeezing so much mass into so small a volume that the escape velocity exceeds the speed of light, and nothing, not even light, can get out. Stellar mass black holes formed this way typically contain between 3 and a few tens of solar masses. They are invisible in themselves, detectable only through their gravitational influence on surrounding matter, pulling gas from a nearby companion star into an accretion disk that glows brightly in X-rays, or betraying their presence through the gravitational lensing of background light. For an extremely massive star like R136A1, the clock runs faster. Within perhaps 2 to 3 million years, its core will have worked through hydrogen, helium, carbon, oxygen, neon, and silicon in succession, building up shells of progressively heavier elements in a sequence that accelerates dramatically as it approaches the end. The hydrogen burning phase lasts millions of years. The helium burning phase lasts tens of thousands. The oxygen burning phase lasts years. The silicon burning phase lasts days. When the core accumulates enough iron, the element at the peak of the nuclear binding energy curve, which requires energy input rather than releasing it when fused, fusion stops. The core collapses under its own gravity in less than a second. What follows is one of the most violent events in the universe. The core collapses to nuclear density, where ordinary matter cannot be compressed further, and bounces, sending a shockwave outward through the infalling stellar material. Combined with an immense burst of neutrinos, ghostly particles so weakly interacting that they can pass through the entire Earth without noticing it, yet so numerous that even their tiny cross-section can help drive the explosion when their density is high enough. That shockwave tears through the outer layers of the star, dispersing them across surrounding space at several thousand kilometers per second. The debris carries the chemical signatures of everything the star produced: hydrogen, helium, carbon, oxygen, silicon, and a rich array of heavier elements forged during the explosion itself. For stars at the very top of the mass scale, death may not follow this pattern at all. Stars above roughly 130 solar masses can undergo what's called a pair instability supernova. At the extreme temperatures reached in such a massive star's core, gamma-ray photons spontaneously create electron-positron pairs. This removes radiation pressure from the core, triggering collapse and an accelerating thermonuclear explosion so complete that it may destroy the entire star without leaving any remnant whatsoever. No neutron star, no black hole, just an expanding sphere of debris carrying the signatures of every element the star produced, dispersed across light years of space. The irony is profound. The most massive stars, the most dramatic objects in the stellar world, may leave the least permanent mark behind. A star containing 200 or 300 solar masses, blazing with the power of millions of suns, may simply cease to exist in a flash, while a much more modest star quietly collapses into a black hole that will outlast the universe. The biggest things go out with the most light but leave the least behind. The more restrained objects endure. How giant stars shape the universe. These objects are not just spectacles, they are among the most active agents of change in the cosmos, and their influence extends far beyond their own locations. The mass that red hypergiants shed through stellar winds doesn't disappear. It drifts outward, mixes gradually with the interstellar medium, and eventually becomes part of the raw material from which new stars and planetary systems form. The winds from VYCMA carry not just hydrogen and helium, but complex molecules, water, carbon monoxide, silicon oxide, that represent the accumulated products of billions of years of nuclear chemistry inside the star. Every ejection event seeds the neighborhood with processed chemistry that would otherwise take far longer to accumulate. When these stars explode, the effect is orders of magnitude more profound. A supernova from a star of 20 or 30 solar masses releases more energy in seconds than the Sun will produce over its entire 10 billion year lifespan. The expanding shockwave compresses surrounding gas clouds, triggering cascades of new star formation in regions that might have remained dormant for billions of years. It carries material enriched with heavy elements outward at thousands of kilometers per second, mixing it into clouds that will eventually form new planetary systems. This connection between a dying star and the birth of new ones is not merely poetic. It is a well-documented physical mechanism called triggered star formation. When a supernova shockwave hits the edge of a dense gas cloud, it compresses that edge, raising the density above the threshold at which gravity can take over and collapse begins. The result is a new generation of protostars forming along the compressed rim of the cloud, potentially decades or centuries after the original explosion. The massive star does not just die, it midwives the birth of its successors. This process has been observed directly in nearby star-forming regions, where rows of young stellar objects can be seen aligned with the direction of expansion from a known supernova remnant, or stellar wind bubble. On longer timescales, this cycling shapes the chemical composition of entire galaxies. A galaxy that has processed more generations of massive stars is a more chemically enriched galaxy, one with more heavy elements available in its gas clouds, more carbon and oxygen and iron for planets to form from, more of the raw material that chemistry and biology require. Our own Milky Way is about 13.5 billion years old, and over that time, it has processed enormous quantities of hydrogen through successive generations of massive stars, building up the heavy element abundance that allowed, among other things, a rocky planet to form in an orbit hospitable to liquid water some 4.5 billion years ago. The heavy elements tell an even more dramatic story. Gold, platinum, uranium, and the other heavy elements near the top of the periodic table cannot be made by ordinary stellar fusion at all. They require what physicists call the RR process, rapid neutron capture, which occurs in one of two places: the extreme environment of a core collapse supernova, or the collision and merger of two neutron stars. In both cases, free neutrons are captured rapidly by existing nuclei, building progressively heavier atoms in fractions of a second. In 2017, a gravitational wave detector first detected the merger of two neutron stars, and follow-up observations of the resulting optical transient, a kilonova, confirmed the production of gold and other heavy R process elements in real time. The R process is responsible for approximately half of all elements heavier than iron that exist in the universe. Every gold ring, every nuclear fuel rod, every heavy atom in the Earth's crust was made in one of these catastrophic events and scattered across space before eventually being gathered into a new solar system. There is also a slower process called the S process, which happens inside stars during their late evolutionary stages. Slow neutron capture builds elements like barium, strontium, and certain isotopes of lead and bismuth in the star's interior. When those outer layers are eventually shed into space through stellar winds or a supernova, those elements go with them. The S process and R process together account for the full range of heavy element abundances observed in the universe, and both depend on massive stars living, dying, and distributing their contents. The iron in human blood was produced inside a star that died before the sun existed. The calcium in bones, the oxygen in lungs, the carbon in every organic molecule. These are the products of nuclear fusion in stars that lived and died billions of years ago. Their debris scattered across space and eventually gathered into the nebula from which our solar system formed. The giant stars are the most prolific sources of that debris. Their short, violent lives and dramatic deaths are not irrelevant to our existence. They are a precondition for it. Without a succession of generations of massive stars enriching the interstellar medium with heavier and heavier elements over billions of years, the chemistry necessary for life as we know it simply would not exist. The universe is a system in which matter cycles continuously. Hydrogen gathers into stars. Stars process it into heavier elements. Those elements disperse when stars die. New stars form from enriched material and build planets. On some of those planets, the chemistry becomes complex enough to look back at the stars and ask where it came from. The limits of what we know. The data we take as fact today is only the available scientific understanding. But the history of extreme stellar astronomy is a history of perpetual revision, and many of these numbers will change as instruments improve. Several of the size rankings of these stars are genuinely uncertain, with candidates sitting within each other's margins of error. The distance to Betelgeuse carries an error of tens of light years. The radius of Stephenson, 2-18, depends on an assumed distance derived from its cluster membership, and if that assumption is slightly off, every derived property changes substantially. The mass of R 136A1 comes from comparing its observed properties to stellar evolutionary models, rather than from any direct measurement, and those models contain their own uncertainties. The James Webb Space Telescope has begun producing new high-quality infrared observations of some of these targets, and its capabilities are genuinely transformative for this field. Webb can observe stellar objects at infrared wavelengths that cut through the dust, obscuration that hides many extreme stars, and it can do so with a sensitivity and spatial resolution that no previous infrared space observatory could match. Already, it has detected molecular features in the winds of evolved massive stars with a clarity that reveals the detailed chemical composition of the material being ejected. Information that tells astronomers not just what the star is shedding, but what nuclear processes in the interior produced it. As more observation time is dedicated to targets like VY Eta Carinae, and the stars of the Stephenson 2 cluster, the picture of these objects will sharpen substantially. The extremely large ground-based telescopes now under construction, with primary mirrors spanning 30 to 39 meters, will resolve features in stellar surfaces and surrounding nebulae that no existing instrument can reach. The European Extremely Large Telescope, being built in Chile's Atacama Desert at an altitude of 3,046 meters, will use adaptive optics systems capable of correcting for atmospheric turbulence in real time, achieving resolutions comparable to what space-based telescopes achieve, but with a mirror area many times larger. It will be capable of directly imaging the surfaces of nearby red supergiants, not just as featureless disks, but as resolved objects showing the convective patterns and surface structures that current instruments can only barely detect. For Betelgeuse, this will mean watching the convective cells evolve in real time, measuring surface temperatures across different regions of the disk, and tracking the ejection events that led to episodes like the Great Dimming with a level of detail that would previously have been impossible. There are also almost certainly extreme stars hiding in obscured regions of the galaxy that have not yet been found. The Milky Way contains between 100 and 400 billion stars, and the regions nearest the galactic center are so heavily veiled by dust that optical telescopes cannot penetrate them at all. Infrared surveys have already revealed entire star clusters, including the one containing Stephenson 2-18, that were invisible to earlier generations of observers. Future infrared surveys with next-generation wide-field space telescopes will systematically map the obscured regions of the galactic plane in ways that current instruments cannot match, almost certainly revealing new clusters and new extreme stellar objects. There is also a growing field called stellar archaeology, the study of old, low-mass stars to reconstruct the chemical history of the galaxy. Because low-mass stars burn their fuel very slowly and can survive for billions to tens of billions of years, some of them alive today were born in environments enriched by the very first generations of massive stars. The chemical composition of these ancient stars, detectable in their spectra, carries a record of what the massive stars that died before them produced. By analyzing large numbers of very old, low metallicity stars, astronomers can reconstruct the enrichment history of the galaxy, one generation of massive stars at a time. In this sense, the giants we've been discussing have left their fingerprints not just in nebulae and black holes, but in the spectra of the most ancient stars still shining, a permanent record of their existence encoded in the chemistry of their successors. What can be said with confidence is that the objects described here represent the known extremes of stellar scale, that they are genuinely remarkable in ways that go far beyond impressive numbers, and that the science of understanding them is very much alive and ongoing. Each new observation adds complexity to the picture rather than simplifying it. And each new generation of instruments reveals layers that the previous generation couldn't see. The very first generation of stars, called Population 3 stars by astronomers, formed from material that was almost entirely hydrogen and helium, with essentially none of the heavier elements that later stellar generations produced. The universe was only a few 100 million years old when they lit up, and the gas clouds from which they formed had not yet been enriched by any previous stellar generation. There was no carbon, no oxygen, no silicon, no iron, none of the heavier elements that act as opacity sources in stellar envelopes and influence how stars form and evolve. Without these heavier elements, the cooling processes that normally limit how large a gas cloud fragment can get before it collapses into a star were far less effective. In a cloud of pure hydrogen and helium, the mechanisms that allow gas to radiate away heat and cool down, a necessary step in fragmentation into individual stellar objects, are much weaker than in enriched gas. The first star-forming clouds may have collapsed as single, massive fragments rather than breaking up into dozens of smaller stars. The result was likely a generation of objects far more massive than anything we observe in the current universe. Models suggest that Population 3 stars could have reached hundreds of solar masses, possibly into the low thousands, before the Eddington limit and radiation pressure halted further growth. They were extraordinarily luminous, burning at surface temperatures far higher than today's massive stars, emitting torrents of ultraviolet radiation that began to reionize the surrounding neutral hydrogen, a process called cosmic rayonization that transformed the large-scale structure of the universe between about 150 million and 1 billion years after the Big Bang. This era, when the first stars switched on and flooded the universe with ionizing radiation for the first time, is one of the least well understood periods in cosmic history, precisely because those stars are gone and the signals they left are difficult to detect across 13 billion light-years. Population 3 stars exhausted their fuel in perhaps a few million years, a geological eye blink in cosmic time. When they died, they seeded the universe for the first time with the heavier elements that every subsequent stellar generation has built upon. Carbon, oxygen, nitrogen, the raw materials of organic chemistry, entered the interstellar medium from those first supernova explosions and began mixing into gas clouds that would form the second generation of stars. Each subsequent generation was born in slightly more enriched material, burned slightly differently, and died to enrich the medium further still. Population 3 stars are all gone now, dispersed and undetectable as individuals. But they started the chain of enrichment that eventually led to population 1 stars like the Sun, to rocky planets, to oceans, and to life. The red hypergiants and extreme massive stars are, in a very real sense, the inheritors of a process that those invisible first giants set in motion more than 13 billion years ago. The largest stars we can observe today are almost certainly smaller than the largest stars of the first generation, because today's universe is richer in the heavier elements that make stellar envelopes denser and more easily blown away. The monsters we can see are, by the standards of the early universe, modest. The true giants of cosmic history are beyond our direct observation, visible only in the legacy they left behind in the chemical composition of everything that exists. The James Webb Space Telescope is currently one of the primary tools being used to search for the signatures of population 3 stars. Looking for the characteristic emission of hydrogen and helium in the spectra of the earliest known galaxies, without the heavier element features that would indicate stellar enrichment has occurred. Whether direct detection of individual population 3 stars or their host clusters is achievable with current or near-future technology remains an open question. But the search itself is pushing the frontier of observational astronomy into the earliest epochs of cosmic time. The view from inside. There is one more thought to consider. When you look at a red hypergiant in an image from the Hubble or James Webb Space Telescopes, what you're seeing is light that left that star hundreds or thousands of years ago. VY shows us its state from around 1400 BCE, the era of the New Kingdom in Egypt, before the fall of Troy. The Betelgeuse visible tonight is the Betelgeuse of approximately 1375 CE, the era of Chaucer and the Black Death. Stevenson, 2 to 18, at 19,000 light-years, shows conditions from about 17,000 years ago, a time when human beings were still primarily nomadic hunter-gatherers, when the ice sheets that would become the North Sea were still intact. The universe we observe is a composite of different pasts, all arriving simultaneously. For giant stars, this time delay carries an extra dimension of significance, because these stars change on timescales short enough to matter. The question of what these stars look like right now has a genuine answer. We just won't receive it for a very long time. Think about what it would actually mean to approach one of them. Imagine you're in a spacecraft, starting from interstellar space, a few dozen light-years out. VY is the destination. At first, it's a point, brighter than the other stars in that direction, deeper in color, but still just a point. As you close in over years of travel at speeds far beyond anything we've achieved, it begins to change. The point takes on a perceptible size. The color deepens from orange to a rich, saturated red. The disk resolves, not sharp and clean like a planet seen through a telescope, but soft-edged, slightly diffuse, the boundary between star and surrounding nebula not entirely clear. Before you even reach the edge of the nebula surrounding VY you'd notice something unusual in your instruments. The interstellar medium, normally almost empty, a handful of atoms per cubic centimeter, would begin to thicken. The density of hydrogen gas would climb, then climb again. You'd be entering the outermost, most diffuse skirts of the material this star has been shedding for the past 1,000 years. In the equivalent region around our Sun, there is essentially nothing. The solar wind has swept it clean, and the surrounding interstellar medium is sparse. Here, in the equivalent region around VY Canis, you'd be flying through an increasingly dense cloud of molecular gas, dust grains, and the signatures of violent ejection events carried outward by the stellar wind. The molecules in this cloud, water vapor, carbon monoxide, silicon monoxide, would be detectable in spectroscopic instruments as distinct chemical fingerprints. You would know, even before the star's disk grew to fill your view, that you were approaching something extraordinarily active. Closer still, and the disk starts to fill a significant portion of the forward view. You can now make out structure in the surrounding nebula, the arcs and knots of ejected material from centuries of eruptions, some of them glowing in faint emission lines, others silhouetted against the brighter glow behind them. The Mars-emitting molecules in the surrounding cloud would be invisible to your eyes, but audible as an intense howl in microwave detectors. The dust torus, opaque to visible light, would show only in infrared, a dark ring surrounding a blazing core. As the disk expands to fill the entire sky ahead of you, you are no longer approaching a star in the conventional sense. You are entering an environment. The photons hitting your ship are not the photons of a single arriving beam from a distant source. They come from every direction ahead of you, from the whole vast surface of a star, hundreds of millions of kilometers across. The radiation pressure alone, even at this distance, would be pushing against you. The stellar wind from VY Canis, denser and faster than anything our Sun produces, would be a constant headwind of plasma, magnetized and structured, carrying the molecular remnants of the star's interior outward at hundreds of kilometers per second. Passing through the outer edge of the surrounding nebula, you'd enter a region of dense dust and gas that would be opaque at visible wavelengths. The star's direct light would be cut off. Around you would be only the dull orange-red glow of heated dust, the entire nebula lit from within by the star's absorbed and re-radiated energy. It would be warm. The dust temperature here is around 800 Kelvin, hot enough to glow dull orange in infrared, hot enough to feel as intense heat, even though the gas is too thin to conduct that energy efficiently. Emerging from the inner edge of the nebula into the region close to the star's photosphere, the environment would change entirely. The dust has been destroyed here, temperatures too high for solid particles to survive. The material broken back into gas and plasma. The photosphere of VY Canis sits at around 3,500 Kelvin at its outer surface, but the opacity gradient is shallow. There's no clean boundary. You'd notice the gas thickening gradually over the course of thousands of kilometers. The light coming not from ahead, but from everywhere around you simultaneously. The source of illumination becoming the medium itself. At the photosphere, the convective motions would be visible as enormous bright and dark patches, each cell spanning distances comparable to the gap between the Earth and Moon. You'd be watching plasma rising and falling in slow motion waves across a surface area millions of times larger than any planet, driven by convection currents that move at hundreds of kilometers per second by our standards, but are glacially slow relative to the star's own size. The magnetic field would be tangled and intense in some regions, smooth and ordered in others, threading through the plasma in structures that shift over timescales of months and years. If you could descend further into the star itself, the density and temperature would climb steadily. At the hydrogen-burning shell around the core, the temperature reaches tens of millions of Kelvin. At the core itself, where silicon is being fused into iron in the final stages of VY Canis' life, it would be in the hundreds of millions of Kelvin. The plasma so compressed that individual atoms have been stripped of all their electrons, and the material exists in a state that has no analogy in everyday experience. A quantum mechanical regime where the pressure is determined not by temperature, but by the quantum nature of matter itself. And then you'd leave, accelerating outward through the photosphere, through the inner atmosphere, back through the nebula's dust and gas, out into the clear interstellar medium. The star would shrink behind you, from all-encompassing wall of light, to glowing disk, to bright point, to one vivid orange-red star among many, to something visible only in binoculars, and finally to nothing, absorbed into the background of the night sky, indistinguishable unless you knew exactly where to look. But as you moved away, you'd still be passing through material VYCMA has shed, the outermost tendrils of its influence extending far into surrounding space. Even thousands of astronomical units from the star, the medium would be measurably denser than ambient interstellar gas. The star's reach extends far beyond its visible disk, far beyond even its observable nebula. It is shaping the medium around it, enriching it, planting the seeds of chemistry that will persist for billions of years after the star itself has gone. You'd be flying through the star's future legacy long after the star had disappeared behind you. Now, change the destination entirely. Instead of VYCMA, point your ship toward R1, 36A1, in the Tarantula Nebula. The approach would be completely different. There would be no gradual deepening of red. As the star resolved from a point, the color would be an intense, eye-searing blue-white. The signature of a surface at 46,000 Kelvin, radiating most of its energy in the ultraviolet. There would be no peaceful approach through thickening orange dust. The radiation environment around R136A1 would be lethal at distances that VYCMA's radiation barely reaches, because the total luminosity is orders of magnitude higher and it peaks in the hard ultraviolet. The stellar wind here is not a warm, molecular-rich flow. It is a gale of fully ionized plasma moving at several thousand kilometers per second, dense enough and energetic enough to have carved the visible cavity in the Tarantula Nebula. Getting close to R136A1 would mean approaching one of the most energetic point sources in the local group. At the same distance that Betelgeuse sits from Earth, R136A1 would outshine the full moon many times over, and would be clearly visible in daylight even without any optical aid. The Tarantula Nebula around it would glow across the sky like the aftermath of an explosion, which in a sense it is. A region of space that has been continuously bombarded with ultraviolet radiation and kinetic energy for over 1 million years. The comparison between the two fly-throughs tells us that extreme in stellar terms does not mean one thing. It means at least two very different things, pointing in opposite directions, both of them beyond the reach of ordinary intuition. The universe is incomprehensibly large, and its most extreme objects remind us, every time we examine them carefully, that our instincts about size and scale are simply inadequate to the task. These stars are not exceptions to the laws of physics. They are physics operating at the edges of its allowed range, producing objects that challenge models, surprise observers, and reveal new phenomena with every generation of instruments. Somewhere in the dust-obscured depths of the galaxy, in the cores of star-forming regions not yet fully mapped, in the stellar nurseries of galaxies 1 billion light-years away, there may be objects larger and more extreme than any we've yet found. The search for them is one of the reasons astronomy keeps going. The giants at the top of the stellar size and mass charts are more than just the biggest things in the sky. They are the universe's most active chemical factories, taking in raw hydrogen, processing it into every element that chemistry and life require, and scattering the results across space in the most violent ways available. They live briefly by cosmic standards, they die spectacularly, and the debris they leave behind goes on to build planets, oceans, and eventually things that can look back and wonder where they came from. We have come a long way from lying under the stars and trying to count them. Every instrument astronomers have built, from the first lenses that resolved the Milky Way into individual stars, to Gaia's billion-star parallax catalogue, to Webb's ability to image stellar objects in other galaxies, has pulled back another layer of what those points of light actually are. For the most extreme stars, each new observation doesn't simplify what we know. It adds to it. New structures appear. New behavior emerges. New questions form around the answers to old ones. That is not a frustration. That is what genuine discovery looks like. The universe doesn't stop being interesting when you measure it more carefully. It gets more interesting. And the stars at the absolute boundary of what physics allows are where that is most visibly, most dramatically, most unmistakably true. If you found this exploration worthwhile, subscribe. We cover topics like this regularly, always going deeper than the surface, always following the science wherever it leads.